This is Gianculli Answers with Mr. Ditchko. Temperature in Kelvin is 273.15 more than the temperature in Celsius. And so we can find the temperature in Celsius is going to be temperature in Kelvin minus 273.15. Then we have this formula for the temperature of Fahrenheit in terms of Celsius. It's 9/5 times the temperature in Celsius plus 32, and then we can plug in what we just figured out for converting from Kelvin to Celsius in for the Celsius temperature here. So we have temperature in Kelvin minus 273.15 is a Celsius temperature written in Kelvin, and then we can plug in and get our conversion to Fahrenheit. So we have 0 degrees Kelvin is absolute zero, minus the 273.15 times 9/5 plus 32 gives negative 459.67 degrees Fahrenheit is what absolute zero is in Fahrenheit. This is Gianculli Answers with Mr. Ditchko. Temperature in Kelvin is Celsius temperature plus 273.15. So the temperature in the center of the Earth is 4,000 degrees Celsius plus 273.15, which is about 4,300 Kelvin. And in the Sun, it's 15 times 10 to the 6 degrees Celsius plus 273.15, which has no real effect because this is such a big number that adding 273 to it doesn't really change the number within our, precision that we have here. So we just write 15 times 10 to the 6 Kelvin. And then the percent error is going to be the temperature in Celsius minus the temperature in Kelvin divided by the temperature in Kelvin. We're dividing by the Kelvin temperature instead of the Celsius temperature because this is like the more correct one. Kelvin is the more rigorous scale to use. It's the SI unit for temperature. So we'll take Celsius minus the reference, like the better one, and divide by that better temperature. So temperature Celsius minus temperature in Celsius plus 273.15 makes negative 273.15 over the temperature in Kelvin times 100% gives the percent error. So for the Earth temperature, it's going to be negative 273.15 divided by the Kelvin temperature for the center of the Earth, and that gives about negative 6.4%. So if you mistakenly state your answer in Celsius, you're going to be 6.4% lower than it should be for Kelvin. And then for percent error for the Sun, is going to be about negative 1.8 times 10 to the minus 3%. And so it's not a big deal if you state the center of your Sun's temperature in Celsius instead of Kelvin, because the percent error is quite small. This is Gianculli Answers with Mr. Ditchko. Initially, at standard temperature and pressure, you have P1 times V1, pressure 1 times volume 1, equals nR times T1. This is the number of moles times the ideal gas constant times the initial temperature. And then you have the same ideal gas law applying in the second case after the temperature rises and the pressure rises. And we can solve for V2 because we know that P1 V1 over T1 is nR. You can divide both sides of this by T1. And you have the exact same quantity of gas in the container after you've squished it. And so P2 V2 over T2 is also equal to nR. And so that makes these two things equal to each other. P1 V1 over T1 equals P2 V2 over T2. So we can multiply both sides by T2 over P2, and then leaving us with V2 on the right, and then this T2 over P2 gets multiplied by the stuff on the left. Then switch the sides around. So we have V2 equals T2 times P1 V1 over P2 times T1. And the only thing to keep in mind is that temperatures always have to be expressed in Kelvin, and pressures are absolute pressures. So at STP conditions, standard temperature and pressure, the pressure is not zero. It's 1 atmosphere. That's the absolute pressure. The gauge pressure is zero, but the absolute pressure is 1 atmosphere. And we'll multiply that by 3.5 times 10 to the times 10 to the nothing, 3.5 meters cubed for the initial volume. And then the temperature is 38 degrees Celsius plus 273.15 to convert it into Kelvin, and divide that by 3.2 atmospheres, and we can leave these pressures in units of atmospheres because the only important thing is that they're the same unit so that they cancel. No need to change them into pascals. And then the temperature at STP conditions is 273 Kelvin. And this makes 1.25 cubic meters as the final volume. This is Giancoli Answers with Mr. Ditchko. Initially in the cylinder you have some initial pressure, atmospheric pressure P1, times some initial volume V1, which we don't know, and then it equals the number of moles of the gas in there times the universal gas constant times the initial temperature expressed in Kelvin. And then after the compression happens, you have some new pressure P2 times some new volume V2 equals nR times T2. And this n does not have a subscript because it's the same molar quantity of gas in both cases. So nR is P1 V1 over T1 if you divide both sides of this by T1, and then we can substitute this in place of nR in the second formula. So we have P2 V2 equals P1 V1 over T1 times T2. And then we can solve for T2 by multiplying both sides of this by T1 over P1 V1. And the P2 V2 gets multiplied by T1 over P1 V1, and the T2 gets isolated, and then we switch the sides around. And so the temperature after compression is going to be the initial temperature 20 degrees Celsius plus 273.15 to convert it into Kelvin times 40 atmospheres after compression P2 times the new volume, which is 1/9 times the initial volume, and divide that by the initial pressure of 1 atmosphere times the initial volume V1. The V1s cancel, and this works out to 1302.89 Kelvin. And if you take away 273.15, we can write this in Celsius. And this kind of explains why diesel engines don't need spark plugs, because after compression the temperature is so high that this can ignite diesel fuel just as a result of the temperature increase because of compression. This is Giancoli Answers with Mr. Ditchko. We're going to solve the ideal gas law for volume by dividing both sides by P for pressure. And we need to keep in mind that pressure is absolute pressure, so it's atmospheric pressure plus the gauge pressure. And this question tells us the gauge pressure of 0.35 atmospheres, and so we have to add 1 atmosphere to that to get the absolute pressure. So V is nRT over P, so that's the number of moles, 16, times the ideal gas constant, 8.314 joules per mole Kelvin, times the temperature written in Kelvin, so it's 10 degrees Celsius plus 273.15, divided by the absolute pressure of 1 plus 0.35 atmospheres. And then we have to convert those atmospheres into pascals by multiplying by 1.013 times 10 to the 5 pascals per atmosphere. And then we get 0.2754 cubic meters must be the volume. And then if the container is compressed so that the volume is now half what it was before, so this is the answer from part A, 0.275425 cubic meters divided by 2. And the pressure is increased so that the gauge pressure is 1 atmosphere, and in which case the absolute pressure is the atmospheric pressure plus that, so that's 2 atmospheres in total for absolute pressure. And then convert that into pascals, and then divide by the number of moles, which is the same. You haven't changed the quantity of helium inside the container, it's still 16 moles. Times by the universal gas constant, and then you get 209.7407 Kelvin. And if you take away 273.15, that gives you your answer in Celsius. So we have negative 63 degrees Celsius. This is Giancoli Answers with Mr. Ditchko. The first pressure when the container contains nitrogen times the container's volume equals the number of moles of nitrogen times the universal gas constant times the temperature written in Kelvin. And we can divide both sides by V, and then also divide both sides by N1. So Vn1 here and Vn1 there. And on the right hand side we're left with RT over V. And on the left side we're left with P1 over N1. And the reason that's useful is because we can rewrite this with the quantities when it is filled with carbon dioxide, in which case we have some different pressure, P2, and some different number of moles, because it's the same mass of carbon dioxide, but the molar mass of carbon dioxide is different, so there'll be a different number of molecules or a different number of moles. And it's still going to equal the same RT over V, however, because the temperature, we're told, is the same, and the container volume will be the same as well. And so since these both equal RT over V, then these ratios will equal each other. So P2 over N2 equals P1 over N1. And we can solve for the pressure in the second case by going P1 over N1 times N2. So P1 is 3.45 atmospheres. That's the pressure when there's nitrogen in there. And we'll multiply it by the number of moles of carbon dioxide. So that's 21.6 kilograms of carbon dioxide divided by the molar mass expressed in kilograms per mole. So to find this, you look in the periodic table in the back cover of the textbook, and it says 12.0107 below carbon, and that is the number of grams per mole. And we multiply it by 10 to the minus 3 to get kilograms per mole. And carbon dioxide also has 2 oxygen atoms in it, so we go 2 times 15.9994 grams per mole for oxygen. And so then this total is the molar mass in grams per mole, and then we multiply by 10 to the minus 3 to get kilograms per mole, and then the kilograms cancel on top and bottom. And it's the same process for nitrogen. Same mass of nitrogen, 21.6 kilograms, divided by 2 times 14.0067 grams per mole, and then multiply by 10 to the minus 3 to get kilograms per mole, and we end up with 2.20 atmospheres. Since we left this pressure in units of atmospheres, our answer is also going to have units of atmospheres.
This is Giancoli Answers with Mr. Ditchko.
We can solve the ideal gas law for volume by dividing both sides by P. And we have the volume is the number of moles of the gas times universal gas constant times the temperature in Kelvin divided by the absolute pressure. So the number of moles of nitrogen is 28.5 kilograms divided by the molar mass expressed in kilograms per mole. And so we look in the back cover of the textbook and you see 14.0067 written in this little square that has nitrogen, and it has atomic mass 7 right between oxygen and carbon. And there's 2 nitrogen atoms per molecule, so we have this times by 2 here. And that's grams per mole, and then multiply by 10 to the minus 3 to get kilograms per mole, so that the kilograms here cancel with the kilograms there. So that takes care of the N, the number of moles. Then we have to multiply by 8.314 joules per mole Kelvin, and then times by the temperature. Now since this is STP, standard temperature and pressure, the temperature is 273 Kelvin. Then we divide by 1 atmosphere, 1.013 times 10 to the 5 pascals. And that gives 22.8 cubic meters must be the volume of the container. Now in part B, we're going to add an additional 32.2 kilograms. So since it's additional, that means the total mass is 32.2 plus the initial 28.5 kilograms of nitrogen. And the volume is going to stay the same for the container. We're just changing the number of moles. And the temperature is the same. So we're dividing this by 2 times 14.0067 times 10 to the minus 3 kilograms per mole, and then times by universal gas constant, and times by the standard temperature, and divide by the volume of the container that we found out in part A. That's 22.795 cubic meters, and we get the new pressure of 2.16 times 10 to the 5 pascals. And we expected this to be higher than it was before, so that makes sense. Because there's now more molecules in here, so we'd expect more collisions between them and more pressure.
This is Giancoli Answers with Mr. Ditchko.
When the scuba tank is on the diver's back, when he's on the boat, it has some pressure P1 times the volume of the tank, times the number of moles of air inside it, times the universal gas constant, times the temperature on the boat in Kelvin. And we're going to divide both sides by N, R, and V, and NR and P1, I should say. And we're going to have the NRs cancel on this side and left with T1 over P1. On the other side, we'll have V over NR, because the P1s will cancel there. And we get T1 over P1, after we switch the sides around, is the volume of the tank divided by the number of moles of air times the universal gas constant. And then once the person jumps into the water, there's going to be a new temperature and a new pressure, but the volume of the tank will stay the same because it's a rigid metal tank, and the number of moles of gas will be the same too, because we're told to neglect, the few breaths of air that the person might have taken en route from the boat to the water. So both of these fractions equal the same thing, so that makes them equal to each other. So T2 over P2 equals T1 over P1. And we can solve for T2, the temperature in the ocean, by multiplying both sides here by P2. And temperature in the ocean is the temperature on the boat times the gauge pressure plus the atmospheric pressure to get the absolute pressure in the ocean, divided by absolute pressure on the boat. So we have 191 atmospheres gauge pressure in the ocean plus the 1 atmosphere to get the absolute pressure, and then divide that by the gauge pressure on the boat, 204 atmospheres plus 1 atmosphere to get the total absolute pressure, and times by the temperature on the boat in Kelvin. So that's 29 degrees Celsius plus 273.15. That gives 282.989 Kelvin. And this number is precise to the ones place, which makes this total have 3 significant figures. And that means this number here has 3 significant figures, and it's therefore precise to the ones place. And then when we take this difference here and subtract 273.15 to turn it into Celsius, the answer here has to be precise only to the ones place, because that's the most precise digit in this number. And so that means our answer is precise to the ones place, and we're forced to round it to 10. 10 degrees Celsius is our answer. That's the temperature of the ocean.
This is Gianculli Answers with Mr. Ditchko.
We solve the ideal gas law for pressure by dividing both sides by volume. You get pressure is the number of moles times the universal gas constant times the temperature in Kelvin divided by the volume in cubic meters. There's a lot of unit conversion involved here. First of all, we have to turn the argon kilograms into a number of moles of argon. So we have 105 kilograms divided by 39.948 times 10 to the minus 3 kilograms per mole. And this number comes from the periodic table of elements in the back cover of the textbook. And all those numbers there for atomic mass can be thought of as grams per mole. And we're multiplying by 10 to the minus 3 to turn it into kilograms per mole. And this gives the number of moles of argon here. And then times by universal gas constant 8.314 joules per mole Kelvin. And then times by 21.6 degrees Celsius plus 273.15 to convert this temperature into absolute temperature, or temperature in Kelvin. And divide that by 38.0 liters times 10 to the minus 3 cubic meters per liter. And we end up with 1.70 times 10 to the 8 pascals.
This is Gianculli Answers with Mr. Ditchko.
Because we have a sealed metal container, we know that the N is going to be constant because it's sealed. And since the container is metal, it's rigid, and so V is constant as well. And we don't need any subscripts on these for the 2 scenarios. So at the first pressure, we have P1 times V equals nRT1. And then when the pressure is increased to 2 atmospheres, we have that second pressure times the same volume equals the same quantity, same number of moles of gas times R times a different temperature T2. And we can rearrange this to solve for T2 and by dividing both sides by NR. And we get T2 is P2 over V, P2 times V over NR. And then from here, we can see that V over NR is T1 over P. If you take this and divide both sides by P1 NR, you end up with T1 over P1, and then it also equals V over NR on the other side. So V over NR is T1 over P1 based on this first equation, and that gets substituted into the second equation, replacing this with T1 over P1. So T2 is P2 from here times T1 over P1, because that's what V over NR is. And that's 2 atmospheres times the temperature in Kelvin, 20 degrees Celsius plus 273.15, and divided by the original pressure of 1 atmosphere. And that gives 282.989 86.3 Kelvin, and minus 273.15 to get the answer in degrees Celsius of 313.